Hi everyone. Today we're going to be learning about the torque generated by an electric motor. We're going to be looking at this quantitatively so that we can actually use equations and numbers to solve problems. What I have here is a photograph of a real motor. We can see that there are a number of different copper little coils in the magnet, in the magnetic field, and these are what will cause the motor to spin. So, suppose we have a loop of current carrying wire like this. How do we calculate how much torque there is caused by this coil? Because that's a big question if we're building a motor, right? We want to know how much torque it can apply. So, we're going to have to give some names to the different parts of the loop. And you can see that I've already put some algebraic letters down here. We're going to call the edge parallel to the magnetic field 2B. Remember that the magnetic field will be going across the diagram like this. And we'll call the side that is perpendicular to the magnetic field L, because that'll help us later on. You'll see why. So why are we calling this side 2B and not just B? Well, you'll see in a moment. So each side of the loop will have a force exerted on it equal to BIL. The sine theta will simply equal 1 because we're perpendicular to the magnetic field. Right, with me so far? So the force is applied at a distance of B from the axis of rotation. And this is why we're using 2B for the whole length. If we're looking at the force on one side of the loop, that is, the force that produces a torque, then the torque is dependent on the distance from the center of this edge of the loop here, because we're looking at the distance from the axis of rotation. Right? Definition of torque and all that. So, using torque equals distance times force, we get a value of lowercase b, that is, this edge, times BIL, the force pulling the edge down. So if the torques on each side of the loop are equal and in the same direction, then we can add the torque produced by this force to the torque produced by this force to get 2B BIL. Right? With me so far? Now, it turns out that 2BL has a special sort of meaning. Can you see what it is yet? Well, we know that the area of the loop is the bottom side, 2B, times the other side, L. Right? That's area. So, substituting area into this equation gives us the total torque being BIA. B is the magnetic field, I is the current, and A is the area of the coil. And it turns out that even if we're not using a rectangular coil, this equation will still hold true. If we have a circular coil, for example, then you'll be able to calculate A with the formula for the area of a circle, which is of course pi r squared. Now, force can only produce a torque when it's acting perpendicular to the axis of rotation, right? Remember that if we have a coil that's tilted vertically, so that the top side of the coil is feeling a force up, and the bottom side of the coil is feeling a force down, then the coil is not going to rotate, right? The force is pulling straight away from the axis of rotation. So what we need is the component of the force that is perpendicular. So including this condition makes our equation torque equals BIA cosine theta. Can you see why that is? Let's have a look. The yellow arrow here, F, is the total force acting on this part of the coil. But we can break that F into two separate components. One of them has been drawn in blue and the other looks like this. Right? It's just like breaking the movement or the motion of a projectile into its x and its y parts. So, looking at this, we can break the total force into the part of the force that pulls away from the axis and the part of the force that pulls perpendicular to the axis. And of course, we can use our trigonometry rules, sine and cosine and that sort of thing, in order to figure out that the magnitude of the blue line, assuming this is a right angle, is going to be the magnitude of the hypotenuse times the cosine of theta, right? And so that will be what's in our equation. This force here is what's causing the torque, not this force here. And of course, if we have more than one coil in our loop, then we're going to have NBIA, cosine theta. And you can see that we just keep adding more and more variables to it, but this is our finishing point. So the torque on a coil with area A and N turns is torque equals NBIA cosine theta. Let's look at an example, shall we? So we take a rectangular coil, dimensions 2 centimeters by 1 centimeter, quite small, and it has 40 turns, and it has its plane parallel to a magnetic field. When 3 amps pass through the coil, what torque acts on it? All right, well, let's work this out, shall we? Our formula for the torque on a coil is going to be torque equals NBIA. Cosine theta simply becomes 1 because the plane is parallel to the magnetic field. Theta is 0, so cosine of 0 is 1. Torque equals NBIA. Right? So let's substitute in some of these numbers. N is going to be 40 turns, so that's over here. B is going to be 0.05, so that's over here. Our current is 3 amps, and our area needs to be measured in square meters, not square centimeters. So our area will simply be this expression here, 1 centimeter times 2 centimeters. It's important to remember that if you take 100 square centimeters, you won't get a square meter. If you take 100 centimeters, you get a meter, so you need 100 times 100 centimeters squared to get a meter squared. 100 times 100 is, of course, 10,000, and not 100. So always make sure you're measuring in square meters, not square centimeters. So, putting these into a calculator, we get an answer of 0.0012 Newton meters. Don't forget that these are the units of torque, not newtons. Example 2. A square coil suspended in a 1/100th of a Tesla magnetic field needs to produce a maximum torque of 0.1 Newton meters. Right? The coil has 100 turns and sides that are 10 centimeters long. And remember, it's a square coil, so both sides will be 10 centimeters long. What current must flow through it to produce the required torque? So in this case, we can once again use torque equals BIA or NBIA, except we need to make I the subject of the equation instead of tau, torque, right? So, rearranging or substituting in our numbers, we have torque, 0.1 Newton meters, N, 100 turns, B, 0.01 Tesla, our unknown variable, and then the area of the coil, right? So we have to be very careful here that we get all the decimal places right, because everything is just 1, 0, right? So, carefully putting these into a calculator and making sure that we have our measurements in meters, we can get an expression for I that looks something like 0.1 over 100 times 100th times a tenth times a tenth, right? And if you're very careful and you evaluate it all out, you'll end up with 10 to the power of 1, 10 amperes. All right, so that's the end of the theory. We've gone through a couple of examples. We've gone through the magnitude of the torque on a current carrying loop. So let's go on to some questions. Question 6. In terms of torque, explain why it is impossible to screw in a screw by hitting it with a hammer, no matter how much force is applied, right? So you can use a hammer to sort of drive a screw into a piece of wood, but you won't be following the little grooves of the screw. So why is this? Well, it's because if you want to produce a torque on the screw, that is, to screw it in, then you need to apply a force that is not parallel to the direction of the axis of rotation, right? You can't just push straight toward the axis. To produce a torque on the object, a force must be applied perpendicular to its axis of rotation, right? So, in the case of a screw, the axis of rotation is going to be straight down the middle, and it turns around that, right? Whereas if we have a hammer, we can't produce a torque sideways like that. We can only produce a torque straight. We can only produce a force straight down, and that's unable to produce a torque. So when a hammer is swung straight down, it produces a force that's parallel to the screw's axis of rotation, which cannot turn it. Question 7. Which of these factors should be changed to change the magnitude of the torque on a coil in a magnetic field? Is it the number of turns in the coil, the height of the magnets producing the magnetic field, the mass of the wire, or the direction of the electric current? So, the mass of the wire might change how fast the coil will spin, but it won't change the magnitude of the torque. The direction of the electric current will change the direction of the torque, but not the size of the torque. And that's what we want to do here. Torque equals NBIA will have the same magnitude whether I is positive or negative. Could it be the height of the magnets producing the magnetic field? Well, that'll make more magnetic field lines, but it probably won't increase the strength of the magnetic field. And that's the B that we need to change the torque. So our answer then is A. From our formula, torque equals NBIA, and N is the number of turns in the coil. So changing this will change the magnitude of the torque. Question 8. A coil PQRS, probably rectangular, has 20 turns and is supplied with a current of 4.2 amps. It lies parallel to a uniform magnetic field of strength 0.028 Tesla. PQ equals 14 centimeters and QR equals 23 centimeters. Right, so we have a rectangular coil, PQRS, right? We have one side PQ, 14 centimeters, and QR, 23 centimeters, right? Except because we're physicists and we always measure things in meters, we're more likely to write down the numbers like this. So calculate the magnitude of the torque that will be acting on the coil. To do this, we need to know the area of the coil. Luckily, we're given its dimensions. I hope by now you can remember the equation that tells us how much torque acts on a coil. torque equals NBIA cosine theta. We're parallel to a magnetic field, so theta is 0 and cosine theta is just 1. It doesn't affect the equation. We can substitute in the other numbers though. For area, we'll have to substitute in the formula for area, right? Length times breadth. So, 20 turns, 0.028 Tesla, 4.2 amps, 14 centimeters by 23 centimeters, times cosine theta. Follow all that? Stick it onto your calculator, and you'll get an answer of 0.076 Newton meters. Part B. State what the coil will tend to do in this situation. Indicate the direction of PQ's motion. So now we have a diagram showing us the direction of the magnetic field. That's B, right? And we also know the direction of the current. It goes in the direction PQRS, as we might have expected. Alright, so how will the coil turn? We can use the right hand rule to figure it out. We can see that the magnetic field will be going this way. And if we look at, for example, PQ, then the current is going upward, so the force on PQ will be in this direction. If, on the other hand, we look at RS, then the magnetic field is still in the same direction, but the current is downwards, so the force on RS goes in that direction. So RS will come forward, and PQ will go in. Using the right-hand rule, the torque pushes PQ into the image, and RS comes out of the image. This means that the coil will rotate on the axis right down the middle here. Right? On to part C. Calculate the torque on the coil when the angle between the field and the plane of the coil is 43 degrees. So now, instead of having a completely flat coil that's parallel to the magnetic field, we have an angle of 43 degrees. So instead of the cosine theta just being 1, it's actually going to factor into the equation now. Other than that, the equation will be the same as it is before. So, of course, we start off with torque equals NBIA cosine theta. Once again, we have 20 turns, 0.028 Tesla, 4.2 amps, and the area of 14 by 23 centimeters. And at the end, of course, we have cosine of 43 degrees. Putting this all into a calculator gives us an answer of 0.055 Newton meters, which, as you can see, is a little bit smaller than when we were parallel to the magnetic field. D. Calculate the value of the torque when the angle between the coil's plane and the field increases to 90 degrees. So in this case, we have the coil turned all the way up to its vertical position. So the force at the top part of the coil is pulling the coil up, and the force at the bottom part of the coil is pulling the coil down. So what's going to happen to the torque? In terms of angles, we can say that the angle between the coil and the field is 90 degrees. And what's the cosine of 90 degrees? Well, it's 0. So, torque equals NBIA cosine theta equals 20 turns times 0.028 Tesla times 4.2 amps times 14 by 23 centimeters times 0. And what will that give us an answer of? Well, it will be 0, of course. So once we're at the vertical position, there is no torque on the coil. There is no turning moment that is trying to make it turn. But that doesn't mean it's not still turning. Remember that when we're talking about force, if a force suddenly stops, it doesn't mean that the object will suddenly stop moving. It'll keep going for a bit. In the same way, if a torque suddenly stops, it doesn't mean that the turning object will suddenly stop turning. It'll sort of carry on a little bit. Which brings us to the next part of the question. E. Describe what will happen if the coil overshoots this vertical position, rotating through an angle of 100 degrees from its position in the diagram. So it started off flat, rotated up to 43 degrees, and then 90. Now it's gone a little bit further than 90. So how will the forces act on it? Well, let's give this a bit of thought. Remember that in the diagram we found that the side PQ went down and the side RS went up, right? So RS was experiencing an upward force, that is a force towards you, and PQ was experiencing a downward force. Now here's my question. Does the direction of the force change after it goes through the 90 degrees? Well, we still have a current, and it's still going in the same direction, and the magnetic field is still going in the same direction. So the direction of the force cannot change. That is, PQ is still being pulled down, and RS is still being pulled up toward you, right? So that means that even if we overshoot our position, the coil is still being pulled towards that vertical alignment. So we can use this information to answer the question. PQ will still be pushed into the image towards the vertical position. So if it overshoots its position, it will move backwards until it reaches the vertical position again. So it might, as it turns, go to the vertical position, overshoot, and then wobble back and forth a bit until it settles. On to the next question. Question 9. Using an appropriate graph, show how the torque on a current-carrying coil in a magnetic field changes as the coil rotates through 360 degrees. That is, a full revolution. Now, we know that if a coil overshoots the vertical position by just a bit, it'll go back the other way, right? That's what we were just talking about in question 9. So that means that the direction of the torque on the coil changes. Can you see why that is? If we're going around in this direction, clockwise, and we overshoot our vertical position, that means that we need to experience an anti-clockwise torque to move back to the vertical position. That means that between the angles of 90 degrees and 180 degrees, we experience a torque in the opposite direction to when we're in between 0 and 90, right? And in fact, this matches up with a sort of mathematical graph that we might already know. It's the graph of the cosine of an angle. It's a maximum at a value of 0 degrees, reaches 0 once it gets to the vertical position, 90 degrees, and then becomes negative as we go from 90 to 180, right? And intuitively this makes sense. Why? Well, the torque is proportional to the cosine of the angle between the plane of the coil and the magnetic field. So that means that the torque on a particular coil will look exactly the same as a cosine graph if we vary the angle between the coil and the field. So all we need to do is draw something like this. So we're basically just drawing the cosine of the angle between the coil and the magnetic field. Don't forget to label your axes. Question 10. A rectangular coil, WXYZ, of one turn, easy enough, has a length XY equals 6 centimeters and a breadth ZY equals 3 centimeters. So it's a bit smaller than our previous coil. It's suspended in a very strong magnetic field that is parallel to XY. A current of 10 amps runs through it. Calculate the magnitude of the force acting on ZY. So what angle will ZY form with the magnetic field? We know that the XY is parallel to the magnetic field. So if we were to draw the magnetic field like this, then XY would be in the same direction. And therefore, so would WZ, right? That means that if we look at ZY, that's going to be perpendicular to the magnetic field. So in this case, theta is going to be 90 degrees if we're to look at the angle of the coil with the magnetic field. So ZY is a line that's perpendicular to the magnetic field, which means it experiences a force. So the magnitude of that force will be F equals BIL sine theta, and that gives us 0.5, that's the magnetic field, times 10, the current, times 0.03, the breadth given in the question. We don't need to worry about sine theta, because if we're at 90 degrees to the magnetic field lines, sine theta simply becomes 1. So putting these numbers into a calculator gets us 0.15 newtons. Part B, calculate the force acting on XY. Now remember, XY is parallel to the magnetic field, right? That means that the angle between the magnetic field lines and XY is 0. So what's the sine of 0? It's also 0. If the edge is parallel to the magnetic field, then there is no force due to the motor effect. C. Calculate the total torque on the coil. So we can do this in two ways. We can either look at the force and calculate the torque from there, or we can use our equation for torque. Torque equals NBIA cosine theta. So if we use this equation, then we take B, 0.5 Tesla, I, 10 amps, A, 3 centimeters by 6 centimeters, and cosine theta. Now remember here, we're not looking at the angle between the magnetic field lines and the side of a coil, like we were in the previous part of the question. We're looking at the angle between the plane of the coil and the magnetic field lines. So in this case, theta will be 0 because our plane lies parallel to the magnetic field lines. We can see this because we know that XY is parallel. So, substituting in our numbers, we have 0.5 Tesla, 10 amps, 3 centimeters, 6 centimeters, and cosine theta will be 1. And putting those into a calculator, we end up with an answer of 0.009 Newton meters. So that's the end of the questions. In this section, we've learned about how we can calculate the torque provided by a current-carrying coil in a magnetic field. We can see that we can use a fairly simple formula in order to calculate this number. Later on, this will become important when we talk about the amount of torque that an electric motor can apply. In the next section, we'll be looking more at exactly how a DC, that is direct current, electric motor works.